Okay, I think we can start. So, good morning, everybody. Good afternoon, everybody, and welcome to this additional session of the Aerospace Engineering PhD seminaries. I'm presenting now on behalf of Manu Soler, that couldn't be here, the coordinator of the PhD seminar series. And we have the pleasure to have with us now Dr. Antonio Concilio from CIRA, that is the Italian Aerospace Center. So thank you very much for having accepted our invitation. And I will be brief. We got basically 35 minutes plus 10 minutes of question. And actually, Antonio earned his degree in aeronautical engineering with honors from the University of Naples, Federico II, and in 1989. And he also got awarded a PhD in aerospace engineering in 1995 from the same university. After that, he moved into business, actually, doing an aerospace business administration master course at ISE Superior Toulouse, France. And then he moved to CIRA, the Italian Aerospace Center, where actually is currently working. And his main research interests are concerning vehicle noise, vibration control, and in particular, adaptive smart structure. And actually, today's lectures is about a general overview and introduction of adaptive structure, what they are and how we can work. And Antonio's got many years of experience with research projects, European, national, and I mean, we try also to get something together, we'll see. So thank you very much. Shut up now, and the stage is yours, Antonio. Thank you once again for...
Thank you, Andrea. And I would like really to express my sincere thanks to Professor Andrea Cini that invited me to be here. You know, it's not usual, at least for me, to have a colloquium of this kind with students from another country, another nation, so another culture, and it's always important to compare the different vision. Someone told me that I have to stay here still. It's difficult for me. I try always to move. And so what is my intention today is to give you some details, a short introduction about what the adaptive structures are. Before speaking about adaptive structures, however, I would like to know if you are well suited with the structures, and in particular, I would ask you, you know, it's a lecture that works on contrary. I am the one that makes questions, and so you have to answer, unfortunately. And what is a structure, in your opinion? May you give me a simple definition of structure? It's an obvious thing. It's all something that is always under our hands, in front of our eyes, but may be difficult to define it. Maybe it's simple. So, who is the candidate to answer? Please, go on. You know, it's difficult to speak about adaptive structures if we do not know what the structure is. Come on. It's something so... Yeah, please, go ahead. Okay, but for doing what? What is the meaning of a structure? What a structure stands for? Yeah, to carry something up and to have an elastic response in that. And then, what else? It is sufficient for you if I have a plastic system and I put on a weight on it. The plastic will deform, so we'll have an elastic deformation, and so answer the definition of the lady upstairs, and it has an elastic, it brings something, but do you define a structure? Do you think that it is a structure? So soft, so deforming? We are approaching the definition. A structure is something that is made to bring some loads with minimal deformation, so to preserve its shape. When we speak about adaptive structures, we are speaking about something that really is a conflict with the definition of a structure itself, because it's something that is done to allow a large deformation. So, while bringing loads and while ensuring the keeping of a shape so that the deformation is limited to a certain extent. So we have the so-called paradox of smart structures. A smart and adaptive structure should be something that is able to carry out a load, is able to deform itself, is able to keep the shape that is commanded to have without without having a great variation. And these definitions are all in conflict one with the other. We have to perform and to have in mind that we have to realize something that is able to change its shape once again, but keeping the shape that we want. One of the easiest way to make an adaptive structure is simply to have something rubber that is very deformable, and so you can give them all the shapes you want. But it is not efficient, because in the way that it is deforming, it deforms also from the external loads, and so you are not able to match your will and the consequence of the incident loads. Then you have to develop some architecture, and you can do that in different ways in order that this paradox is overcome, this apparent paradox is overcome. One of the things that you can do, and this is the thing that we do inside CIRA, I work as Andrea, thank you again, told I'm working within the Italian Aerospace Research Center, is to use the actuators as bearing elements in order to give the structure the possibility to being stopped in certain deformation. But it does mean that you have the elements, the actuators are load-bearing elements, are structural elements. They stop being a characteristics, let me say, machine to allow movements of something, but it has to carry out a load. I mean, an automatic door does not carry any load apart the weight. Instead, you have something that has to carry out a load, the aerodynamic load for adaptive wings, for instance. And in that way, you have also something that should resist. This implies a lot of things, like the one that the actuator should be sized in order to allow this kind of loads to be born, and a complication in the structure itself. But the message is that you have a structure and an actuator and the actuator chain that is all the structural system. You have no more a structure and an actuator and a sensor. You have something that is complete. You have something that is complex and overall works like a system, like a structure. If you go in the bibliography, you can find out this definition of adaptive structures that dated 2002, made from Macare, a sort of association for standards in Europe concerning aeronautical structure. And they define the adaptive structures as a structure that is equipped with sensors, actuator intelligence to give them autonomy, adaptation capabilities for reducing operational costs of instances. So they also define the aim of an adaptive structures, but this part of the definition may be skipped within the definition of adaptive structure itself. And this is something that works, and we can consider it current up to our days. But I would like that you reflect on something. If this definition is correct, and we understood that and adaptive structures is made of different systems that are combined all together, then we have no more a simple structure, something that is static, that cannot be deformed, that is allowed just to bear weight and loads. You have something that is capable to modify itself, to have different properties, and so more than a static structure, you have a machine. Okay? We are moving from, let's say, from the skyscraper to a transformer robot, just as a vision. But that is the way. You have a structure that is deforming. You have a structure that is a machine. And please remind this word, because I am going to show you something that replies very well this kind of concept. And it's very common, it's very similar to the robotic world. In a sense, we can say that with adaptive structures, we are approaching the robotic world in another way, but maybe this can be discussed in further meetings. One thing that I am particularly proud of that is that one definition of ours was reported in the Science Direct website for a month. They changed the reference to the different articles that are published throughout the world. And they took this definition from two colleagues of mine, Ignazio Di Mino and Rosario Pecora. One is a colleague of mine at the Italian Aerospace Research Center. The other one is a colleague at the University of Napoli, Federico II. And they published this work within that book that is proudly published by us through SVA and Butterworth Heinemann. That is a book on shape memory and law engineering. I'm not making any advertising here, but it's just a bibliographic reference. The main thing of that book is that it collects the works from 50 scientists, 40 Italians and 10 worldwide, that works together with on the matter of shape memory and laws. We will define shape memory and laws in few minutes. And the most important thing, apart the content, and why I am particularly enthusiastic about that experience, is that these 50 colleagues did trust in us and allow us to collect their works and to make this publication. So it's something that, I don't know, it happens once in a life, for me at least, and so I showed you. As you can imagine, adaptive structures may be very, very wide thematics. You can have adaptive structures everywhere, and if you consider what is my definition of adaptive structures, I say my because any one of us can have one, and it can be better than mine, can be different from mine. No one has the right response. But adaptive structures are everywhere. In, let's say, in a prototypic version, your chair is an adaptive structure. The flap of an aircraft is an adaptive structure. And many other things. This laptop, you can close it, is an adaptive structure. What is the difference between all these things and the future of the adaptive structures? Is that these things are very complex, occupies very large volumes. You see the volume that is necessary to host the actuators of a flap that is outside of the architecture of the wing, so that you have some protection to hide these actuators, and so to let that the aerodynamic flow is not affected by the presence of that systems. It's very large, it's very heavy, it's very room consuming, and the perspective of an adaptive system is to be compact, in first issue, to hide everything inside. And in this sense, you can imagine two different kinds of adaptive structures. One that are both figured out in this view of an adaptive aileron that we manufactured and tested in Canada at the National Research Council, Wind Tunnel. It was a cooperation with the École Technique Supérieure de Montréal and CIRE and University of Napoli. Well, we developed the aileron. The aileron had a continuous shape there, and here you can see the hidden kinematics. So you can imagine two different kinds of adaptive structures. One is transformer one. Let's simplify it. So a sort of robotic structure with all junction, hinges, arms, and stuff like that. And another one is Terminator 2 robot that is continuous. That is usually known in literature as compliant structure, something that is fluent, has no discontinuities, okay? And if you cover this kinematic structure with a continuous skin, able to resist the external loads and preserve the shape, then you have realized what is a compliant structure through a kinematic system. I have no information about an adaptive structures today that is not made from a kinematic inner structure. It may be more or less complex, more or less minimal, more or less invasive, but you have always a kinematic structure. And the skin today is the largest challenge for making a true adaptive structures to work and to operate. Because this kind of skin shall have very conflictual, as usual, properties. When you speak about adaptive structures, you are speaking about conflicts. Systems that should do something and should do the opposite at the same time. The skin shall be elastic enough to be deformed without any effort from the actuators, so shall be stretched very, very easy. Otherwise, you are bringing other work to the actuator system that has also to deform the skin, and shall be resistant enough in the vertical sense. So in the bending, it has to be very, very stiff. And this is very, very complicated to obtain. Let's say that while the most of the adaptive systems in this sense, the desk, the chair, are already ready for commercialization. But the adaptive systems of this kind, let's say we are speaking about a technological readiness level of 5 to 6, if you all of you know what a technological readiness level is. But it does mean that they are pretty ready for being tested in operational condition, in general condition, without any specific and peculiar attention. While for the skins, we are speaking about a technological readiness level between 2 and 3. That means just the first step before a significant test in laboratory and wind tunnel condition. So, as I told you, adaptive structure world is very, very wide. And we at CIRE, at the Italian Aerospace Research Center, do not have experience on all the branches of the adaptive structure. I don't think that anyone has. So we focused on 3 particular aspects. One is noise and vibration control. There are good reasons why noise and vibration control is the first application of smart structure systems in literature, at least as we now consider the smart structures or adaptive structures. It's a bit different, the two terms, but let's consider that like the ones. Monitoring system, basically structure with embedded sensor networks for sensor monitoring, for monitoring of the health, for shape reconstruction and for the monitoring of electromechanical systems. Because, there is on this point, I would like to spend some words, because there is a lot of time, a bit of confusion, in my opinion, concerning the structural health monitoring. Structural health monitoring means that you are monitoring a structure that is something that brings loads by allowing small deformation, okay? And the monitoring of electromechanical systems that are made basically from rigid parts that are not made to be structured, are just made to be kinematic systems. I'm speaking, for instance, about landing gears. The landing gear is a complex machine. We used to put sensors on that in order to monitor the energy that enters the landing gear, and so to have an idea of what is the fatigue degree of that kind of system. We are not making structural health monitoring. We are not monitoring strains in order to understand how the structure is affected from the strain, but how much energy is entering the system, and so in its wool, it's providing fatigue to the system. And so to understand if that landing gear is able to resist for a longer life than predicted, than designed, or should be substituted before. For instance, if a military pilot, maybe a fresh military pilot, used perhaps to land very, very hard, and so the fatigue of that the landing gear shall absorb, the fatigue level that landing gear shall absorb to each landing is very, very high. A professional pilot of a civil aircraft lands softer than the one before. So the same landing gear would be very resistant for the latter one, and should be very excited from the action of the former. It does mean that irrespectively of the design, you should change the landing gear before for, let's say, a younger pilot, and after for an older pilot. But you have to measure that. You cannot decide abruptly. There are a lot of things that can happen. Weather condition, speed, velocity, speed, and other stuff, lateral wind, and other stuff. So that, in this case, you should take into account effectively what is the amount of energy that enters the landing gear. Once you get it, you know if you have to substitute it or not. Something that now is scheduled for a substitution each 20,000 hours of flight, usually, just to give you a reference number. But it happens that sometimes the landing gear broke before, or the landing gear could be used for other 20, I'm exaggerating, 20,000 hours, flight hours, no? Or 20,000 landing. And so there is the necessity to understand what is the energy that enters. And you can do that by an integrated system that should be embedded within the structure without affecting an essential system for the flight, that is the landing gear. So the complexity is to insert a sensor network within it without modifying its actual response. Something that I would like to define before we can go to some more practical examples. I hope to have some minutes to perform these examples, to show these examples. Is that an adaptive structures or smart structures can use smart materials, but it's not necessarily use smart materials. I mean that what I showed you here morphing systems, systems that are able to change their shape without any visual impact from the outside. You do not see any kind of actuation or sensor or other stuff, but simply a structure that deforms itself. Use a commercial actuation system, commercial sensors, without any kind of developments. It's a standard architecture. Smart materials are something that can transform external energy into a mechanical energy. Okay, let's give this simple definition. And they are good candidates for making compact actuators, but you do not need to use smart materials to make a smart structure. You can use commercial actuators. The advantage is obvious. You use certified actuators, you buy them on the market, and you skip all the difficulties that you can have in certifying those kind of actuators that are not commercial but in development. Okay? The most suitable candidates are piezoelectric ceramics that are able to transform electrical energy into mechanical energy, shape memory alloys that transform thermal energy into mechanical energy, and others like magnetorological fluids. But in that case, more than a transformation of energy into mechanical energy, you have a transformation of the state of the magnetorological fluids that moves from real fluids, usual fluids, to pretty solids by changing their viscosity as a function of the magnetic field outside. And for like an extension, you can talk and you can speak also about fiber optics for their capability of easy integration within a generic structures. But they are not the essential elements. Here you can see some examples of smart structures that are made with the use of smart materials, but they are not the only one. All these examples were performed at CIRA for vibrationless control. For de-icing protection, you can use the capability of transforming electrical energy into mechanical energy to produce wave at very high frequency within a structure, so to detach the ice from the wing. In this case, we are speaking about de-icing. There are also the anti-icing protection systems that avoid the ice to be formed on the structure. In this case, we speak about de-icing. In other words, to remove the ice from the structure. Shape memory alloys for realizing morphing system or for modifying the dynamics of a plate. In the same way, you change the sound is produced by your guitar by changing the stiffness within the wires of shape memory alloys, and you also can modulate this difference. Shape memory alloy is a fantastic material that is the most classical one is nickel titanium one, or nitinol, because it was first manufactured at Naval Ordnance Laboratory some time ago. That is a metallic alloy capable to have a deformation of the 8%. 8% means that you have a rod of 1 meter, and by applying a thermal load, you can reduce this length to 92 centimeters. You can imagine what is the force that you need to reduce the length of such rod. If you don't believe me, you can try. And you will find some difficulty, I guess. And so they are capable to develop extraordinary forces. However, since you are applying thermal loads, you have something that is basically static. So you cannot use them for dynamic application, but you can use them for static deformation that induce a dynamic variation in sense of dynamic property variation. In this case, the stiffness, the variation of the stiffness of the shape memory alloys produces a modification in the dynamic response of the plate, and so you have new eigenvalues, new eigenvectors, new modal shapes. Okay, just a few examples for noise and vibration control. This is what we realized some time ago concerning the application of a combined system of piezoactuators, piezoelectric actuators. In this case, sensors were made by accelerometer, placed all over the structure, and some those brilliant part. I don't know if I can use the pointer, but in the upper part of the screen, you can see that those silver-like structure. It's sound-absorbing material. By combining active, passive, and stuff like that, we reduce the noise and vibration field of this case for electronic scarf protection by something like 10 dB in the range between 100 and 900 Hz. So really a wide spectrum of reduction. Some other examples regarding the active noise radiated by windows that is very difficult to realize, because a window is something that you cannot cover with anything. Otherwise, you lose the window. your system is useless. And so you have to act on the border, like in that one, in that example. In this case, we used the piezoelectric actuator stacks for giving the frame a sort of counter vibration to reduce the vibration that otherwise would have radiated noise outside of the box that we used as a test article. Some application on cars, shape reconstruction. This is the example I spoke about before concerning the smart landing gear. So a landing gear that is equipped with the sensor networks to record the strain that is produced at landing, but also on the ground, because have you ever considered that no one knows about the real weight of an aircraft at the takeoff? No one can know it. No one asks the passengers to be weighted before entering an aircraft. So apart the luggage that you weight on the balance at the embark, but the personal luggage and yourself are not weighted. So no one knows how much an aircraft weighs or where the barycenter is, the center of gravity is. And this can be a problem. Another problem concerns the real information concerning the exact instant when the wheel detached from the ground. That is important because in the first case you have some weight that is transferred to the ground. In the other case, the machine, the helicopter, the aircraft is free to move. But if the wheel touches the ground, then you could have a moment in making some maneuver, and some accidents happened for this reason. These are examples of health monitoring systems performed by the use of fiber optics, both distributed and concentrated. Distributed fiber optics means that you have a very, very dense networks of sensors, each 1 or 2 millimeters, very, very dense. FBG are more distributed, let's say 1 sensor each centimeter for a limited number of sensors, but the difference between the first and the second is that the first you can use at ground because it cannot fly. The optics is very, very sensitive to movements and to vibrations, so you cannot fly with that. The other one can be flown, and so it is used currently for developing flying structural health monitoring systems. I'm just making some fast overview of what were our experiences, and let's complete it with two messages. One is that to arrive where we are now, we are performing some. You can see that image that is named AG2 is a European project, and we are going to perform flight test on the next year. The date is wrong. The project will end on 2023 because we experienced some difficulties in making all the checks for making the system to fly. And now we are approaching that target, finally. Some good example of adaptive structures that were tested full scale. Another problem concerning the adaptive structures is the scaling of them. It could be nice to discuss about it, but please, let's have a look in bibliography concerning the scaling of adaptive structures. And in Saristu, where we realized that together with many other partners, an adaptive wing made of a leading edge, an adaptive leading edge, an adaptive trailing edge, an adaptive winglet. Particularly, we were focused on the development of the adaptive trailing edge, together with other 10 partners. The wing that you can see there at far right is 5.5 meters long and was tested in Russia in 2015. And when I talk about machine, this is the adaptive trailing edge as we developed it. Here on the top left, you can see what was the prototype that was realized very close to here at Arnova engineering plants. And you can see that the structure is no more a simple structure, but is really a machine with fiber optics cables, the yellow ones, the electric cables for feeding the actuators, the electric actuators that are the green wires, and all the different parts that makes this sort of flap, trailing edge, the last part of the wing, a sort of a finger. And here you can see the same prototype. Once the skin that was produced by Fraunhofer Bremen was installed on it in order to give them some continuity in the shape. And all this was mounted on the Saristu adaptive wing with the 3 adaptive parts realized. The wing box was manufactured by Leonardo Aircraft, and all the project was coordinated by Airbus Deutschland, Airbus Germany. That more or less is a milestone in our developments. And just to conclude, I spoke about AG2, I spoke about Saristu. Another interesting project led by my colleague Salvatore Meduri is this one that is Sabre, concerning the development of an adaptive blade for helicopters. And in this case, we can see how smart materials, in this case shared memory alloys, can be used effectively for realizing an adaptive structures. Really, that is the only choice. Because a blade, an helicopter blade that is long something like 4 or 5 meters and is large, just 20 centimeters, with a thickness of a few centimeters, cannot allow to put mechanical actuators inside. You have no room for that. You cannot put the actuators outside of the blade. Otherwise, you would not have a blade anymore. And so the only way is to use smart materials that are able to change your input, your electrical input, into a mechanical action. This is the example, I repeat again because it's important, where you need a smart materials to realize a smart structure, in this case an adaptive structure. Because you have weight constraints, you have room constraints, and other stuff that force you to use this kind of system. This system was realized and up to now has been tested in the wheel tower at the DLR and into a wind tunnel at the University of Bristol that were partner of Sabre. The Sabre was an European project where a lot of partners, not only CIRA, performed and realized their own devices to be mounted on helicopters. I'm just speaking about what was our realization. But again, in bibliography, if you are curious, if you are interested, you can find some more materials on that. I think that the time is over, unfortunately. I would like to know if there are questions. Please do that. For who is interested or want to make some discussion with me, I'm here in the afternoon, so you can walk the other way. And so, many thanks for your attention. I hope that I did not annoy you too much. Thank you again to have been here.